In this lecture, we are going to define one more term, which deserves its own lecture. So far, I told you that the goal of the agent is to maximize the reward it gets. But as you recall, the reward may be structured differently in different games. For example, in tic-tac-toe, you may receive a +1 for winning or a -1 for losing. On the other hand, if you're solving a maze, you might get a -1 at every step. So what does it mean to maximize the reward? Does it mean to maximize the reward at the next step, or does it mean to maximize the total reward over an entire episode? Here's the answer. To state it more accurately, the goal of the agent is to maximize the sum of future rewards. Why is that? Well, it can't maximize the rewards it got already. Those are in the past. They cannot be changed. Furthermore, we don't want to only maximize the reward on the next step. What if we are solving a maze and we get a -1 for any step we take? In that case, the agent isn't incentivized to do anything useful, because no matter what it does, the immediate reward is still -1. Thus, the agent's true goal is to maximize the sum of future rewards until the episode is over. In this way, the agent is planning its future steps as well. It must have some concept of where it will end up, because that's the only way it will know how to maximize rewards in the future. To take a real-world example, consider again the idea of preparing for a math exam. For a math exam, you don't receive any reward until you've completed the exam. The reward signal is your grade on the exam. But imagine all the actions it will take to actually maximize that reward. You'll have to study, you'll have to do homework, you'll have to forego socializing with your friends. In fact, all of those actions do not sound very rewarding at all. And thus, if your only incentive is immediate gratification, in other words, the rewards you will receive immediately, then you will not do well on your math exam. Instead, you must make use of long-term planning. Sure, I may not want to study today. It may be very annoying, and I will miss my favorite TV show. But because you are planning long-term, you're not thinking only about today. You're thinking about the results of your math exam. The desire to maximize the total future reward is necessary for long-term planning. We call the sum of future rewards the return. We describe the return mathematically using the symbol g. Because it depends on future rewards only, it is time dependent, so we index it with a t. We can say the return at time t is the sum of rewards at time t+1 up to the terminal state at time at big T. Now you might be wondering, what happens if we have an infinite horizon MDP, a game that never ends? In this case, your return might be infinity. Therefore, we introduce a concept known as discounting. Discounting is used for infinitely long tasks, but it's also used for episodic tasks as well. We introduce a discount factor called gamma. Each future reward is weighted by gamma to some power. Gamma is usually a number close to 1, like 0.9, 0.99, or 0.999. It's a hyperparameter, so you'll have to choose its value based on the performance of your agent. The idea is, the further you go into the future, the harder it is to predict. Therefore, we care a little more about getting rewards now than we do later. Intuitively, this works just like money. I would rather receive $100 today than receive $100 10 years from now. In 10 years, $100 will be worth much less than it is today due to interest. One important feature of the return, which we will make use of throughout the rest of this section, is that it can be defined recursively. In other words, in terms of itself. Specifically, the return at time t is equal to the reward at time t+1 plus gamma times the return at time t+1. This may not seem like much more than a simple math substitution now, but you'll see how it'll become very useful later on.